Welcome back to the deep dive. Today we are standing on the edge.
Ideally, not literally.
No, not literally, but metaphorically. We're talking about boundaries. You know that moment where a system just shifts?
Right.
Like on one side, everything is vibrating and energetic, moving like a wave, and then you cross this invisible line and suddenly everything just changes. It gets quiet. It decays.
That is a very poetic way to describe what's called a turning point.
I try, but seriously, we are looking at a specific mathematical concept that describes exactly that transition. It's called the Airy function. And I know you just heard function and might be reaching for the skip button, but don't do it, because this isn't just dry calculus. This is the math of rainbows.
It is, and it's the math of quantum mechanics and these strange beams of light that seem to curve all on their own. It is a surprisingly beautiful bridge between two very different worlds of physics.
So we have a stack of notes here, primarily based on the Wikipedia entry for the Airy function, which actually goes into some serious depth on the history and the heavy math.
Yeah.
Our mission today is to decode this.
Yep.
We want to understand how one little equation acts as this bridge you mentioned. So let's start with the name, Airy. Is it named that because it describes air, or?
It's actually named after a person, Sir George Biddell Airy.
Oh, okay.
He was the British astronomer royal back in the 19th century.
Okay, Astronomer Royal. That's a cool title.
It is. And like a lot of scientists of his time, he wasn't just looking at stars. He was obsessed with optics, how light behaves. But before we get to the history, we really have to look at the beast itself, the equation.
Right, the Airy equation, or the Stokes equation, as it's sometimes called. I'm looking at it here, and it looks deceptively simple. It's just y double prime minus x, y equals 0.
Exactly. yxy equals 0.
Exactly. yxy equals 0.
Okay, let's unpack this. For anyone who hasn't done calculus in a while, y double prime, that's the second derivative, that describes curvature, right? Or acceleration. Correct. In physics, the second derivative tells you how the function is bending. If you think of a graph, it's the concavity. So the equation says that this curvature is equal to x times the value of the function itself.
And that simple relationship creates this whole turning point behavior.
It does. And this is why mathematicians love it. It is considered the simplest second-order linear differential equation that has a turning point. But to see why, you have to sort of play with the variable x.
Okay, I'm game. Let's say x is a negative number. We're on the left side of the graph.
If x is negative, say minus 5, then the equation becomes y double prime equals negative 5, y, or y double prime plus 5y equals 0.
Wait, I recognize that structure. Acceleration equals negative position. That's a spring.
Exactly. It's the equation for a simple harmonic oscillator, a spring bouncing back and forth, or a wave. The curvature is always pulling the function back towards 0.
So when you look at the graph of the Airy function on the left side, where x is negative, it's wiggly. It oscillates.
Precisely. But notice what happens as you go further left into more negative numbers. The spring gets stiffer, you could say, because x is a bigger negative number.
So the waves get faster.
Yes. The frequency increases, and the amplitude, the height of the waves, gets smaller. It's a nervous, fast ripple.
Okay, so on the left, we have ripples. Now, let's cross that line. What happens when we hit 0, when x becomes positive?
That is the turning point. At x equals 0, the sign flips. Now you have y double prime equals xy, where x is positive.
So the curvature isn't pulling it back to 0 anymore, it's pushing it away.
Exactly. If the function is positive, the curvature bends it more positive. If it's negative, it bends it more negative. It stops oscillating, it becomes an exponential function.
And exponential usually means it just takes off, right? Or crashes.
In the case of the main Airy function, which we call ai of x, it crashes. It decays rapidly. It just slides down towards 0 and fades away.
So if you were to draw this, on the left you have these ripples, and then they hit this invisible wall at 0, and the ripples just smooth out and die off into a long tail on the right.
That is the perfect visualization. And that is why it's so important in physics, because in the real world, boundaries are rarely hard. If a wave hits a wall, it doesn't just stop instantly at the atomic level. It penetrates a little bit. It decays.
Yeah.
The Airy function describes that soft boundary where oscillation turns into decay.
That is fascinating. It's like the mathematical description of fizzling out.
In a way, yes. But here is where it gets really interesting. Differential equations like this usually have two solutions. We call them linearly independent solutions.
Right, I saw this in the notes. We have ai of x, which is the good one we just talked about, but then there's an evil twin.
I wouldn't call it evil, but it is certainly unruly. The first solution is ai of x. It's well behaved because as x gets bigger, it goes to 0. That makes it physically useful.
For things like probability or particles trapped in a box.
Exactly. And the second one?
The second one is called B of X, BI.
BI.
Okay, what does B do?
On the negative side, the wave side, B looks just like AI. It oscillates with the same amplitude, just shifted in phase a bit. But on the positive side, where AI politely fades to 0,
Yeah.
B explodes.
Explodes.
It grows exponentially to infinity.
Oh, wow. So if AI is the fizzle, B is the kaboom.
Basically.
Yeah.
And because it shoots off to infinity, it's often discarded in simple physical problems where you need a finite answer. You can't have a probability of finding a particle that is infinity, you know?
So why do we keep it around? Why not just delete it from the textbooks?
Because mathematically, you need it to form a basis. You can't define the general solution to the differential equation without it. And sometimes you are describing a system that grows. So B is the necessary partner, even if he's a bit loud.
Got it. The unruly sibling stays in the picture. Now, let's pivot back to the man himself, George Biddell Airy. You said he didn't invent this just to torture calculus students. He was looking at rainbows. He was. And not just the cartoon rainbow. He was studying something called the supernumerary rainbow.
Supernumerary? That sounds expensive.
It does. Have you ever looked at a really bright rainbow and noticed that just inside the main violet band, there are these faint, repeating pink and green bands?
I think so, like echoes of the rainbow.
Exactly. Those are supernumerary rainbows. Classical geometric optics, just drawing lines for light rays, couldn't explain them. According to simple ray theory, the light should just stop at the edge of the rainbow.
But it doesn't.
No. Light is a wave, and waves interfere with each other. Airy was trying to calculate the intensity of light near a caustic.
Define caustic for us, because I usually think of caustic wit or acid.
In optics, a caustic is an envelope of light rays. It's where light rays bunch up and focus. You know when you shine a light through a glass of water and you see that bright curved shape on the table?
Yeah, that sharp curve of light.
That's a caustic. A rainbow is essentially a giant caustic in the sky. It's a fold in the light intensity. Airy realized that near this edge, the intensity of the light doesn't just cut off. It oscillates and then fades.
Wait, oscillates and then fades? That sounds familiar.
It is exactly the Airy function. He developed this math specifically to describe how the brightness of the rainbow ripples near that edge.
That is so cool. So he writes this down in, when was this?
1838.
1838. He writes down the math. Was he right?
He was. A few years later, in 1841, a physicist named William Hallowes Miller tested it. He didn't have a convenient rainstorm, so he used a thin cylinder of water to simulate a raindrop and shone light through it. He observed 30 of these tiny, dark and bright bands, these supernumerary bands, and they matched Airy's theory perfectly.
I love that. 30 bands. That's precision.
It is. And interestingly, Airy didn't call it the Airy function at the time. The notation AI of X was actually introduced much later by a geophysicist named Harold Jeffreys, but the name stuck to Airy.
As it should. Okay, so we have rainbows. That's a beautiful classical application. But the outline says this function is a heavy hitter in quantum mechanics, too.
Oh, absolutely. In fact, for a modern physics student, the Airy function is almost synonymous with quantum mechanics.
Why? What's the connection?
Think back to the shape of the function. Ripples on one side, decay on the other. In quantum mechanics, particles behave like waves.
Right. Wave-particle duality.
So imagine a particle trapped in a potential well, specifically a triangular well. Imagine a floor that is sloped, like a ramp, and a hard wall on one side.
Okay, so the particle can bounce against the wall, but as it goes up the ramp, a force slows it down until it stops and slides back.
Exactly. Classically, there is a specific point on the ramp where the particle stops and turns around, a turning point.
There's that phrase again.
In quantum mechanics, the particle is a wave. On the ramp side, before the turning point, the particle has energy, so its wave function oscillates. That's the wiggly part of A of X. But past the turning point, where classically it shouldn't be able to go.
It tunnels.
It tunnels, it penetrates into the forbidden region, and that penetration is perfectly described by the decay tail of the Airy function.
So the Airy function is literally the map of a particle hitting a soft wall.
Exactly. It solves the Schrödinger equation for a particle in a constant force field like a constant electric field. It is the textbook description of a boundary in quantum mechanics.
This brings me to something else in the notes. The WKB approximation. The notes call it a uniform semiclassical approximation. That is a mouthful. What does it actually mean?
This is where the Airy function does some heavy lifting. In physics, we often can't solve equations perfectly. We use approximations. The WKB method is a way to approximate the wave function when the properties of the environment are changing slowly.
Okay, so it's a shortcut.
Yes, and the shortcut works great when the particle is moving fast, far from the turning point, or when it's deep in the forbidden region. But right at the turning point, the approximation breaks.
Why does it break?
Because the approximation relies on the momentum of the particle. At the turning point, the velocity goes to zero. The wavelength effectively tries to become infinite. The math it blows up. You get a divide by zero error.
So the shortcut fails exactly where the action is happening.
Exactly. So physicists use the Airy function as a patch. They know that locally, right near the turning point, the system looks like the Airy equation. So they solved that little section using AI of x and then glued it to the WKB solutions on either side.
It's the duct tape of quantum mechanics.
A very elegant, high-precision duct tape, yes. It connects the oscillating world to the decaying world smoothly without the math blowing up.
I love the idea of a patching function. Now, I want to talk about one application that jumped out at me from the notes. This accelerating beam in optics. This sounds like sci-fi.
This is one of the coolest modern applications. It was theoretically proposed and then realized in the lab around 2007. Imagine a laser beam. Usually light travels in a straight line, right?
Rule number one of light. Light travels straight.
Well, scientists created what they call a transversely asymmetric optical beam. Basically, they shaped the cross-section of the beam so that the intensity profile looks exactly like the Airy function.
So a bright peak on one side and then those fading ripples on the other.
Exactly. When you launch this beam, something bizarre happens. The main brightest peak appears to curve. It accelerates to the side.
It curves. Like a banana kick in soccer.
Yes. It creates a parabolic arc as it travels through free space.
But physics, conservation of momentum. You can't just have light turn left for no reason. It needs to bounce off something.
Physics is safe, don't worry. This is where the tail of the Airy function comes in. Remember that long tail of ripples on the other side?
Part that fades out.
Yes. As the main bright peak curves one way, that low-intensity tail spreads out and curves in the opposite direction.
Oh, I see. So the average position of the light is still going straight.
Exactly. The center of gravity of the beam travels in a straight line, satisfying conservation of momentum. But visually, and in terms of where the energy is focused, the beam effectively bends around corners.
That is wild. So you could shoot a laser beam around an obstacle.
In principle, yes. They're called Airy beams. They are also non-diffracting, meaning they don't spread out and get fuzzy as fast as normal laser beams.
Just because they used this specific math shape.
Because the Airy function has these special properties of stability. And get this, it's self-healing.
Self-healing. Like Wolverine.
A little bit. If you place a small obstacle in the path and block the main bright peak, the tail, because it contains the phase information of the whole function, will actually reconstruct the main peak further down the line.
No way. The tail grows a new head.
It does. The interference pattern reforms the Airy shape.
Okay, my mind is officially blown. We went from a 19th century astronomer looking at rainbows to self-healing, curving laser beams that fix themselves if you block them.
And we aren't even done. It shows up in probability theory, too.
Right, the random matrices. This seems like a totally different field. We're leaving physics now and entering statistics.
We are. Random matrix theory deals with the statistics of huge grids filled with random numbers. It turns out, if you look at the distribution of the largest eigenvalues, the most important numbers describing these matrices, they follow a specific pattern.
And let me guess, it's Airy.
It's the Tracy-Widom distribution, which is defined using the Airy function.
Why Airy?
Oh.
Where's the turning point in a random grid of numbers?
It represents the soft edge of the spectrum. The eigenvalues are packed together like a fluid, and at the edge of that fluid, the density drops off. That drop-off is described by the Airy function.
So it's a boundary, yeah.
It's always a boundary. This pops up in everything from nuclear physics to the behavior of the stock market to how distinct interface growth happens, like how a coffee stain spreads or how a Tetris game fills up.
The Airy function describes Tetris.
In a very abstract statistical way via the KPZ equation. Yes. It describes the fluctuations of the surface growth. If you drop blocks randomly, the roughness of the top layer follows statistics governed by the Airy function.
It really is the boundary function. Wherever there is an edge, Airy is there.
That is the big takeaway.
Before we wrap up, I do want to dip our toes into the deep part of the notes, the mathematical nuances. We talked about AI and bi, but the notes mentioned Bessel functions. Are they related?
They are cousins. The Airy functions can actually be written in terms of Bessel functions of fractional order, specifically order 1/3.
Why 1/3? Is that arbitrary?
No, it comes from the cubic nature of the phase. Remember the integral definition of the Airy function. It involves t cubed over 3. That cubic term is the signature of the Airy function. When you do the math, that cubic power translates into the order 1/3 in Bessel world.
Which leads to the Fourier transform, right?
Right. If you take the Fourier transform of the Airy function, basically asking what frequencies make this up, you get a complex exponential with a cubic phase, e to the I key cubed.
So in the frequency domain, it's a cubic.
Yes. And that cubic phase is why it's so important in describing dispersion, how waves spread out. The Airy equation essentially describes a system with cubic dispersion.
And there's this thing called the Stokes phenomenon. It sounds like a ghost story.
It can be a nightmare for mathematicians. We said earlier that AI of x decays exponentially when x is positive, but that's only strictly true along the real axis.
Meaning, if we stick to normal numbers.
Right. But if you step off into the complex plane using imaginary numbers, the behavior gets complicated. Depending on the angle you look at the function in the complex plane, it might switch from decaying to growing.
Wait, so if I just rotate my view in the complex plane, the fizzle becomes an explosion.
Exactly. These sectors where the behavior flips are separated by lines called Stokes lines. It means you have to be very careful when you use approximations because the rules change depending on your angle of attack in the complex plane.
It's like a hall of mirrors.
Very much so. But that complexity gives it its power. It allows it to connect different physical regimes.
So what does this all mean for us? We've got an equation, y double prime minus xy equals 0. We've got rainbows, quantum tunnels, curving lasers, and random matrices.
I think the lesson is about the universality of mathematics. Airy wasn't thinking about semiconductors or lasers in 1838. He was looking at a drop of water. But because he rigorously described the geometry of that turning point, he created a tool that unlocks the physics of boundaries across the entire universe.
It's the tool for soft boundaries.
Exactly. Nature rarely deals in hard, instantaneous stops. Things fade, things transition, and the Airy function is the map for that transition.
I love that. So next time you see a rainbow, look for those faint extra bands on the inside.
The supernumerary bands.
And realize you are looking at the Airy function in the wild. And think about that accelerating beam of light.
Yeah.
It's a lovely image to leave on light, bending around a corner, guided by math from the 1800s.
It really is.
Thanks for diving in with us. We'll see you on the next one.
Goodbye.